All right, let's dive into a classic algebra problem. You know, when you need to find a number way down the line in a sequence, but you really don't want to do all the tedious work to get there. Well, let's get right into the shortcut. So imagine this. You've got a simple pattern of numbers, and you need to find, say, the 100th one. What's your first thought? Probably just to start adding or subtracting over and over again until you land on it, right? But honestly, who has the time for that? I mean, calculating 99 individual steps, it's not just boring, it's the perfect place for a tiny mistake to sneak in and throw your whole answer off. There has got to be a better way. Yeah, that slow, step-by-step method actually has a name. It's the recursive method. And doing it that way really can feel like you're just stuck on the stairs, climbing every single one just to get to a higher floor. And this is the perfect way to think about it. The recursive method. That's the stairs. Sure, it's reliable, but man, is it slow. The explicit formula, though, now that's our elevator. It takes you directly to exactly the floor you want to go to, no stops. So let's push the button and call that elevator. The explicit formula is our powerful tool, our express pass for jumping straight to our destination in any of these arithmetic sequences. And here it is. Some people even call it the teleporter formula, which is pretty awesome. Let's break it down real quick. A sub n is just the term you're looking for. A sub 1 is your starting point, the very first number. D is the common difference, the number you're adding or subtracting each time. And n is the term number, like that 100th spot in line we were talking about. Okay, let's talk about the elephant in the room, that little n-1 part at the end. It's the part that trips a lot of people up. It seems a little weird, right? But I promise, there's a really simple logical reason for it. And this shows it perfectly. Think of it like you're walking. You're already standing at the first term, right? You haven't taken any steps yet. To get to the second term, how many steps do you take? Just one. To get to the third term, you take 2 steps. See the pattern? The number of steps you take is always one less than the number of the spot you're trying to reach. So to get to the 100th term, you gotta take 99 steps. That's all that n-1 is. All right, enough with the theory. It's cool, but let's see how this elevator actually works in real life. We're gonna walk through a couple of examples, starting with a nice, easy one. So here's our first sequence, 4, 7, 10, 13, and on and on. Now, our first job isn't even to find a specific number. It's to build the master key, the special formula just for this one pattern. First, we gotta find our pieces. Our first term, A1, that's easy. It's right there, it's 4. Now for the common difference, our D, well, how do we get from 4 to 7? We add 3, so our D is 3. Now we just plug those pieces into our teleporter formula. So we have an equals 4 plus 3 times n-1. When you distribute that 3 and clean it all up, you get this beautiful, simple final version. An equals 3n plus 1. That's our control panel for this elevator. And here's the magic. Now that we have that custom formula, we can find any term we want. So let's use it to find the 50th term. All we have to do is plug 50 in for n. So we just take our formula, 3 times 50 plus 1. Well, 3 times 50 is 150, plus 1 is 151. Boom, done. See? We didn't have to count 49 different steps. We just took the elevator straight there. All right, you ready to try a trickier one? Let's kick it up a notch. Check out this sequence. 100, 93, 86. Notice it's going down. This is a big clue because it means our common difference is going to be a negative number. Okay, let's do the same thing. Find our parts. The starting point, A1, is 100. And to find the difference, D, what do we do to get from 100 to 93? We subtract 7. So our D is negative 7. So we build our formula, AN equals 100 plus negative 7 times n-1. After we simplify that, it becomes AN equals 107 minus 7n. Now we want to find the 15th term, so we plug in 15 for n. That's 107 minus 7 times 15, which is 107 minus 105. And the 15th term is just 2. Now, using the formula is one thing, but knowing where the hidden traps are is just as important, right? So let's go over a couple of the most common pitfalls that can catch you off guard. Here are the 2 big ones. First, people accidentally mix up n and d when they're plugging numbers in. Just remember, n is the position in line, d is the step size. The second one?
forgetting to distribute correctly. This is huge, especially when you have a negative d. You have to make sure you multiply it by both things in the parentheses. It's such an easy mistake to make, so watch out for it. So you might be asking that classic question, when am I ever going to use this in real life? Well, believe it or not, this formula is probably more useful than you think. How about with your money? Seriously, a simple interest savings account is a perfect real-world example of an arithmetic sequence. Every single year, your money grows by a fixed, predictable amount. Let's play it out. Say you start with $100. That's your A1. You decide to add a fixed $5 every year. That's your D. And you want to know how much money you'll have in 30 years. That's N. I mean, who really wants to sit there and add $5 29 times?
Exactly, nobody. We just use the formula. It's 100 plus 5 times 30 minus 1. So that's 100 plus 5 times 29, which gives us $245. Instantly. You know exactly where you'll be. That's the power of the elevator.
And just to leave you with one final thought, does this formula look kind of familiar to you? If you've ever worked with linear equations, y equals mx plus b, well, this is pretty much the exact same idea, just dressed up differently. The common difference d is just your slope m, and your starting value is kind of like your y-intercept. It's all connected. Makes you wonder what other connections are hiding in math, doesn't it?